Welcome back, everyone. Today, we are going to take a brief but important step backward in time. Over the last several lectures, we explored the incredible power of Fourier transform infrared spectroscopy or FTIR. We learned how modern spectrometers use interference and interferograms and Fourier mathematics to rapidly generate highly accurate infrared spectra, but before computers became powerful enough to perform rapid Fourier transform, spectroscopists faced a major challenge. They still needed a way to separate infrared radiation into individual wavelengths, and they had to do this mechanically. This led to the development of dispersive IR instruments. Although FTIR dominates modern laboratories today, many older research facilities and teaching laboratories still contain these classical instruments, and understanding how they work is extremely important. Why? Because these systems represent a remarkable period in the history of optical physics and analytical chemistry. They are masterpieces of mechanical and optical engineering. Now take a look at figure on the screen. Immediately you can see that instrument appears far more mechanically complicated than FTI systems we discussed earlier. There are numerous mirrors, moving parts, beam pathways, mechanical linkages, and control systems. And unlike FTI spectroscopy, there is no interferometer. Instead of an interferometer, the core component is the monochromator. Inside the monochromator, that is reflection grating. The monochromator physically separates infrared radiation into individual wavelengths. Unlike FTI systems, which measure all wavelengths simultaneously, dispersive instruments isolate and measure one wavelength at a time. This means the instruments must mechanically scan across the infrared region step by step. As you can imagine, this process is much slower. Let us now carefully follow the radiation path shown by the dashed lines. The infrared source emits broadband radiation. Immediately, the beam splits into two separate pathways, the sample beam and the reference beam. The reference beam passes through a mechanical device called an attenuator. This attenuator can partially block the beam. We will soon see why this is important. Next, both beams encounter a rotating device called the chopper. This rotating chopper is one of the most fascinating components of classical IR instruments. So, what exactly does the chopper do? The chopper rotates continuously at a relatively low frequency, typically between 5 to 30 Hz. As it spins, it alternately directs the reference beam and the sample beam into the monochromator. In one position, the chopper reflects the reference beam into monochromator. A fraction of a second later, the rotating opening allows the sample beam to pass through. This alternating cycle repeats continuously. Why is the beam alteration is necessary? Now here is critical important point. Infrared detectors are extremely sensitive to thermal radiation, and it's not just the IR radiation coming from the source. The detector can also respond to ambient heat, thermal radiation from the instrument housing, and even heat emitted from the nearby components. Remember, everything above absolute zero emits infrared radiation. That includes metal caching, optical mounts, laboratory air, and even the instrument itself. This unwanted thermal radiation creates background noise. The rotating choppers solve this problem beautifully because the beam alternates at a specific frequency. The detector output becomes an alternating electrical signal oscillating at the exact chopper frequency. The amplifier is specifically tuned to amplify signals only at that frequency. This allows the instrument to distinguish the true IR signal from random thermal background radiation. This is an incredibly elegant engineering solution, especially considering these instruments were designed long before modern digital electronics. Now observe another important detail in the diagram. The sample and reference compartments are positioned before the monochromator. Why is this arrangement important? Because suppose the sample itself emits unwanted infrared radiation, or suppose scatter radiation emerge from the sample compartment. If this stray light enters the monochromator, the grating disperses it. Only the desired wavelength reaches the detector. This greatly improves the spectral purity. Now, let us examine the thick black lines shown in the diagram. These black lines represent the mechanical linkages. This is where the instrument becomes truly fascinating. Dispersive instruments use a system called optical null balancing. The idea is surprisingly clever. What happens during absorption? Suppose the sample absorbs infrared radiation strongly at a certain wavelength. Now the sample beam reaching the detector becomes weaker than the reference beam. This creates an imbalance. The detector senses this difference and generates an electrical signal proportional to the imbalance. That electrical signal activates a synchronous motor. The motor physically moves the mechanical attenuator into the reference beam pathway. This blocks part of the reference beam until the sample beam and the reference beam once again becomes equal in intensity. When the detector sees equal intensities, the signal returns to zero. This is called a null condition. Now comes the remarkable engineering part. The movement of the attenuator is mechanically linked to a pen recorder. As the attenuator moves, the pen moves across the chart paper, physically drawing the infrared spectrum. Imagine that for a moment, the entire spectrum is being generated through mechanical motion, feedback motors, optical balancing, and synchronized scanning. It is an extraordinary achievement of pre-digital engineering. But despite their elegance, dispersive instruments suffered from serious limitations, and these limitations ultimately led to the rise of FTI spectroscopy. First limitation is response lag. Because the system relies on physical moving parts, it cannot respond instantly. The motor and attenuator require time to move. Suppose the spectrum contains a very sharp absorption peak, the system may not react quickly enough. The pen recorder physically lags behind the true signal. This creates distorted peak shapes. Every moving mechanical component has inertia. The heavier the system, the slower the response is. This limits scanning speed and spectral accuracy. Second limitation is overshooting. Now let us examine another problem, that is overshooting. Because the attenuator and the motor possess momentum, they may continue moving slightly beyond the correct balance time. The pen can overshoot the true absorption value. This produces artificially deep or distorted peaks. Sometimes the system may even oscillate around the correct value before stabilizing. This further reduces spectral accuracy. Third limitation is poor accuracy at low transmittance. This is perhaps the most serious issue. Suppose the sample absorbs extremely strongly, very little radiation reaches the detector. Now the detector signal becomes extremely weak without sufficient signal strength. The feedback system struggles to operate effectively. As a result, the strong absorption peaks become rounded, sluggish, and inaccurate. Deep valleys in regions such as 1700 cm inverse or 3000 cm inverse often appear distorted. Since the monochromator scans one wavelength at a time, data acquisition is inherently slow. Recording a full spectrum may take several minutes. In contrast, modern FTIR instruments can acquire spectra in seconds. That is the fourth limitation, it is slow data collection. Why the FTIR replaced dispersive instruments? And this is exactly why the scientific community transitioned toward FTIR spectroscopy. FTIR replaced mechanical scanning with mathematical transformation. Instead of gears, motors, choppers, and moving attenuators, modern spectroscopy relies on interferograms, digital sampling, matrices, and Fourier algorithms. The result is faster measurements, higher sensitivity, better resolution, and vastly improved accuracy. Let us summarize today's lecture. The dispersive IR instruments physically separated IR radiations using monochromators and diffraction gratings. They relied on rotating choppers, mechanical attenuators, synchronous motors, and optical null balancing systems. Although they were brilliant engineering achievements, they suffered from major limitations, response lag, overshooting, poor low transmittance accuracy, and slow scanning speeds. These limitations ultimately drove the transition toward modern FTI spectroscopy. In our next lecture, we will continue exploring infrared instrumentation by examining infrared radiation sources and IR detectors, also known as transducers. We will see how spectrometers generate infrared radiation and how detectors convert invisible molecule transitions into measurable electrical signals. Thank you for watching. I will see you in the next lecture.